Welcome back, students. In the previous videos, we talked about the intervals of increase and decrease and the nature of critical points, local maximum, local minimum, and neither. Now let's discuss the concavity. So we are done with these, and let's talk about the concavity. And here's the conclusion. The second derivative is positive, or the first derivative is increasing. These two are equivalent. Why are these equivalent, by the way? The derivative is positive, then the original function is increasing, but if this original is f prime already, then this will be f double prime. So if double prime is positive, that means f prime is increasing. It follows from here as a matter of fact. Same goes down here as well. Second derivative is negative, or first derivative is decreasing. They're equivalent. Again, from the same observation down here. We start from f prime, then the derivative of f prime is f double prime down here, and that's what we are getting over here. In that case, what happens to the original function? We have concave up and concave down respectively. It's easy to remember. Up is up, down is down. Above the x-axis, that's up. Function is going up, that's up. And concave up, that's up. Here's a visualization. All these are concave up. Bent upward, bent upward, bent upward. Here, concave up while increasing, concave up while decreasing. Here, concave up while decreasing, hit local minimum, and increasing. We can consider various situations. In this particular case, let's look at this animation here. Please pay attention to the red line segment, which is a segment of the tangent line, and look at its slope. It is very negative right here. Let's see how it changes. Hit 0, and then increasing, and gets bigger. You see? Very negative, and gets bigger, and hits 0, and slope is now positive and getting still bigger. Let's see, very negative, and increase to 0, positive, still increasing. You see? The first derivative function is increasing, and thus we have concave up. Here was a nice visualization. How about the other way around? These are three examples of concave down. Graph is bent downward. Concave down while decreasing. Concave down while increasing. Here, concave down with local maximum and keep like this. And again, here's a visualization here. Starting line segment here, we have very positive slope, and the slope will gradually decrease. Okay. Oh, I didn't mean to stop the animation. Slope is decreasing, and becoming negative, very negative. Again, start with very positive, decrease, hit 0, and negative, keep on decreasing. Slope is decreasing. Do you see that? Don't look at the y-coordinate. Look at the slope. Slope used to be very positive. Now gets down, 0, and becomes negative, and keeps getting smaller. That's associated to concave down. Conclusion. Second derivative is positive, above the x-axis, up. First derivative is going up. Original is concave up. Up is up. Second derivative is below the x-axis, down. First derivative is going down. Original is concave down. Down is down. It's easy to remember. Now if the concavity changes at some point, that kind of points are called inflection point. Up to here, concave up, inflection point, now concave down. Up to here, concave up, now inflection point, concave down. Concave up, now concave down, those kind of points. Here's a visualization, I think. Let's see. Let's slow down a little bit. Okay, I can see. Concave up and hit this point on the y-axis, and then from that point on, concave down. Concave up, from here, concave down. Now look at the slope. Slope is increasing, 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 inflection point, now decreasing, decreasing, decreasing. Increase, 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 now decrease, 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 decrease. That's what inflection point is. Another way to see inflection point, second derivative has to be 0 because you see we have to have a critical point of the derivative function. Derivative, let's get this animation again, excuse me. Again, let's look at this. This is, as a matter of fact, local maximum of the derivative. Derivatives increase, 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 and then decrease. Derivative is going up, 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 now down, down, down. The slope is going up, 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 now going down. So this is local maximum. In order to have local maximum, we have to have the derivative 0. So derivative of derivative is second derivative. So we have this. But as a matter of fact, what we are really looking at is, this is actually just a sufficient condition, just a necessary condition. What you're really looking at is inflection point is actually you're looking at the local extremum of f prime. So local maximum or local minimum of the derivative function. Second derivative is 0. Well, first derivative may end up with neither maximum nor minimum. In that case, it's not going to be an inflection point. What we are really looking at is local extremum of f prime. That is really the key. So this condition over here, even though our textbook author emphasizes a lot, it's not really, it's not everything. It's not sufficient. It's just necessary. This is what you're looking for. Local extremum of the derivative. Okay, ready to go to an example problem. Let's do it in the next video.